Welcome to my channel Physics with Akash Goel. In the last lecture on semiconductors, we have seen what are the semiconductor materials, what is the energy band theory, and how semiconductor material are different from the conducting materials, what are the free electrons, what is n-type and p-type semiconductor, what is intrinsic semiconductor. This all we have seen in the last lecture. Let us do some problems on the previous lecture. The problem statement says the concentration of whole electron pairs in pure silicon at this particular temperature is 7 into 10 to the power 15 per cubic meter. So this is the number of electron hole pair per cubic meter at this temperature in pure silicon. Antimony is doped into silicon in a proportion of 1 atom in 10 to the power 7 atom. Assuming that half of the impurity atoms contribute electrons in the conduction band, calculate the factor by which the number of charge carriers increases due to this doping. The number of silicon atoms per cubic meter is 5 into 10 to the power 28. So what is the initial number of charge carrier? Let us write it as n initial. So this is the number of pairs. Just double it, multiplied with 2, it is 14 into 10 to the power 15. This is the total number of charge carriers, which includes number of electron and number of holes. So this is the total number of charge carrier per cubic meter. Now antimony is doped, and what is the concentration in which antimony is doped? 1 atm in 10 to the power 7 atoms, and we have total number of silicon atoms per cubic meter is 5 into 10 to the power 28. So number of antimony atoms, a number of doping atoms. So number of doping atoms is equal to 5 into 10 to the power 28. This much is the number of silicon atoms, and multiplied by 1 by 10 to the power 7. So this is 5 into 10 to the power 21. So this much is the number of doping atoms. Now it is given that half of the impurity atoms or doping atoms contribute electrons in the conduction band. So number of electrons contributed by these doping atoms. So number of electrons contributed. So this is half of this. This is 2.5 into 10 to the power 21. So this much is the number of electrons contributed. Now what is the total number of charge carriers? So this is, let's say this is n final, and this is equal to new number of electrons plus new number of holes. Now we can say in these situations the number of electrons contributed by this is almost much larger than the number of electrons due to the broken bonds. So we can say that this much number of electrons are almost all the electrons are contributed by this doping atom. So this Ne dash is approximately equal to 2.5 into 10 to the power 21, and these all electrons are contributed by these impurity atoms. And in this situation the number of holes is decreased also, and this number of holes is much less than the number of electrons, because as electrons are increasing, so there is a chance of recombination, and this chance of recombination is increased too much now. So there is a increased chance of recombination, and the number of holes are now much less than the number of electrons. We can also confirm this from this relation. This Ne dash into Ns dash is equal to Ni square. This is the law, and from this law we can easily see that Ns dash is much less than this Ne dash. So n final we can simply write it is approximately equal to this Ne dash. So we have to find the factor by which the number of charge carrier increases. So that factor, suppose that factor is lambda, and this is equal to this Ne dash divided by Ne plus Nh, which is the initial concentration, and this will become 2.5 into 10 to the power 21. And what is the initial concentration? 14 into 10 to the power 15. So the answer is approximately 1.8 into 10 to the power 5. So we can see that the number is increased too much, 1.8 into 10 to the power 5 times of initial by the impurity atoms. Next question. The mobility of electrons in a semiconductor is defined as the ratio of their drift velocity to the applied electric field. So Vd divided by electric field is defined as mobility. If for an n-type semiconductor, the density of electrons is, the density of electron we denote it by a small n, this is 10 to the power 19 per meter cube. And their mobility, we are given the value of mu here also. Mobility is this much, then resistivity of the semiconductor, since it is an n-type semiconductor, contribution of force is ignored. So n is equal to this much, this is just equal to the number of electrons. So we have to find the resistivity of this semiconductor. So we can use this relation. The current density is J is equal to this electric field divided by resistivity, and this J we can write it as any Vd. And for Vd we can write it equal to mu into E. This Vd is equal to this mu into E. So Vd and E, this is mu into E. So E and E will be cancelled, and this resistivity is simply equal to 1 divided by any mu. And I think all the data are given. N is given, E is the electronic charge, and mu the mobility is given. And if we put all this data, we will easily get the answer as 0.4 ohm meter. So correct answer is the choice number 2. Next question. The product of the hole concentration and the conduction electron concentration turns out to be independent of the amount of any impurity doped, and the famous relation is the product of electron concentration and hole concentration is equal to Ni square. This is equal to the intrinsic concentration square. The concentration of the conduction electron in germanium is this much. So obviously this is the intrinsic concentration. When some phosphorus impurity is doped into germanium sample, the concentration of conduction electrons increases to this much. So this is your Ni, and this is now Ne. Find the concentration of holes in the doped germanium. So obviously you have to use this equation. This is Nh is equal to Ni square divided by Ne. And what is this? This is 6 into 10 to the power 19 whole square, and this Ne is now 2 into 10 to the power 23. So solving we can get 1.8 into 10 to the power 16. So this is the whole concentration, and we can easily see the whole concentration is very less as compared to the electron concentration. Now let us take the next topic in semiconductor, and the topic is p-n junction. So till now we know what is p-type semiconductor, we know what is n-type semiconductor, and now this is p-n junction. P-n junction, as the name suggests, it is a junction of p-type material and n-type material, but we cannot take it like this, that we took a p-type material, we took a n-type material and just combine them. So if we just combine a p-type material and n-type material, then it won't serve our purpose, it won't be a p-n junction, because there will be no interaction between these two portions. There is no atomic interactions, there is no flow of electrons and anything between these two. These two will behave like a separate or independent entities. So it is not just a simple p and n junction. We cannot just combine p and n and we will get p-n junction. So this is not the process by which we get the p-n junction material. The p-n junction is fabricated or formed using some metallurgical process. So we have to use some metallurgical process, and by that only we can get the p-n junction. So it is a metallurgical process. Using metallurgy concepts we form or fabricate p-n junction. And to form or fabricate a p-n junction, what we do? By properly doping impurities in a semiconductor material, one can make p-type and n-type region in the same wafer or sheet which meet at a planar layer. This system is called p-n junctions. So to make p-n junction, we can take, suppose this is n-type. Let's say this is n-type material or n-type sheet or wafer, and in one portion of this n-type material. Suppose if this is n-type, obviously the impurities are pentavalent impurities, and suppose in this portion I diffuse trivalent impurities, so that this becomes p-type. So I diffused trivalent impurities in such a concentration, in such a number, so that it becomes overall p-type. So this boundary forms the p-n junction, and usually in diagrams we just show this part, we just show this much part like this, and we show the junction like this. This is, we say this is p side and this is n side. So using this kind of metallurgical process we form p-n junction, and in this kind of p-n junction, here we have trivalent impurities or acceptor atom impurities. In this side we have pentavalent or donor atom impurities. So it is donor atom impurities, and this is trivalent impurity region, and there may be a concentration difference. We can have trivalent concentration more than this pentavalent concentration. So concentration of acceptor atom and concentration of donor atoms may be same or may be different on the two sides. Depending upon our use, we can form such kind of p-n junctions. Now, what are the processes which are occurring in a p-n junction? There are two main processes which are occurring at the p-n junction. One process we know as diffusion, and other process we know as drift. So there are two main processes. One is diffusion, other is drift. So let us first take the diffusion process. What is this diffusion process? Due to concentration difference at the junction, and this is the typical p-n junction. In one side we have acceptor atom impurities in large number, and at the other side we have donor atom impurities in the large number. So this side is p side and this side is n side. Overall this material is neutral. There is no charge, there is nothing. So overall this material is neutral, because to make p-type semiconductor we have doped silicon solid with some acceptor atom impurities, and obviously there is charge neutrality. There is no net charge. There is no net charge also here. So there is no charge anywhere. There is no charge density, nothing. So due to concentration difference at the junction, so at this junction, on one side we have holes in the large number, and on one side we have electrons in the large number. So due to concentration difference at the junction, this is natural. What is natural? Holes and electrons diffuse across the junction due to this concentration gradient or concentration difference. Obviously holes will diffuse from p to n and electrons will diffuse from n to p. So holes will diffuse from p to n and these electrons will diffuse from n to p. So across the junction these holes will cross like this, and across the junction these electrons will cross like this due to this concentration difference. What happens due to this kind of diffusion? So due to this kind of diffusion, the thing which happens is something like this. So this is the material, and now we have suppose this is our junction initially. This was the p-n junction initially, and we have suppose this kind of region in between. Obviously this is again p side and this is n side, and across this junction electrons moved from n to p, and as electrons moved from n to p, it recombine with the hole and electron hole pair is now destroyed. This hole which was near this junction on the p side, this hole moves to the n side and it recombines with the electron, and in that way electron and holes or electron hole pair is destroyed. So in this particular region which is near the junction, a layer or a region is developed. In this region Now there is almost no electron hole pair. Hole from P just moved to this side, and in moving to this side it recombined with the electrons, and electron hole pair of this region are destroyed. Electron from here moved to this, and electron and holes are combined, and in this way electron and hole pairs are destroyed in this region. So in this whole region there is almost no electron hole pair. Obviously there will be 1, 2, 3, maybe a very negligible number of electron hole pairs, because at any instant electron hole pairs are generated. Recombination recombination will go on. And since this region is now charge carrier free, there is no electron hole pairs, there is almost no electron hole pair in this region. This region is now known as depletion layer or depletion region. So diffusion makes the region near the junction carrier free. There is no electron hole pair in this region. This is known as depletion region or depletion layer. But what happens next is positive charges appear in the depletion layer on the n side, because as you can see the holes are moving here, holes are going there, and if holes are reaching here, holes is like a positive charge, so here positive charge density will increase in this region. And since electrons are moved like this, so electrons are reaching here, and the negative charge density here is increased. We can also talk in other terms like electrons are moving from N to P, and electrons are leaving their pentavalent atoms behind. And since electrons are leaving their pentavalent atom, that pentavalent atom is now positively charged. So we will get positive charges here, and these positive charges can be thought of from this pentavalent ionized atoms. So pentavalent ions, because electrons leave this place and electrons moved to P side, so we will have a positive charge density here. And again we will have some negative charge density also. So this region has some negative charge density. So in the depletion layer or in the depletion region, so this region is of our interest. In this region this is carrier free, but this region is not charge free now. Overall the material this complete material is neutral, there is no charge overall. But in this region is now carrier free, there is no electron hole pair in this region, but there is positive charge here and there is negative charge here. We will get some space charge density. So positive charges appear in the depletion layer on the n side. On the n side there we will have positive charges, and negative charges appears on this P side as on the figure. There is no space charge density in the depletion region, and there is no electric field. So since there is a charge here, charge separation or whatever it is, so plus minus are created, and due to this plus minus there will be electric field from positive to negative charge. So this is the electric field created. So this is the electric field, and due to this electric field multiplied by some distance will give you potential difference. So there is potential difference across the junction. So due to diffusion this kind of things are happening. We will have depletion layer, depletion region, which is charge carrier free, but now it has some space charge density, and due to this space charge density we will now have some electric field, and due to electric field we will now have some potential difference in this region. Now let us take a question. A hole diffuses from P side to N side. As we have studied, there is a diffusion, and diffusion is due to concentration difference. We say a hole diffuses from P side to N side in a PN junction. This means that, so the question wants to ask us about what is actually happening, because there is no such kind of thing as we know as hole. Hole is not a physical thing. We just talk in terms of hole. Actually there is movement of electrons, there is no movement of hole, because hole does not exist. Hole is just our imagination. We talk in terms of hole in the valence band. So a hole diffuses from p side to n side. What is actually or physically happening in the material? This is asked in this question. So this is the p-n junction. Here we have p and here it is n, and a hole is diffused from p to n, and hole is now here. What actually happens is a bond is broken on the n side. A bond is broken, that means an electron is free from here. So electron is freed from here if bond is broken on the n side. So electron freed from the bond jumps to the conduction band. So obviously this is not the case, because in that case electron is just free from here and it is just filling the valence band. It is just filling the conduction band. A conduction electron on the p side jumps to a broken bond to complete it. Conduction electron on the p side. Conduction electron on the p side jumps to a broken bond to complete it. And which broken bond? It is not saying about that. A bond is broken on the n side. So in the option C, a bond, there are some kind of bonds here and one of the bond is broken. So one bond is broken, electron is freed. Electron freed from the bond jumps to a broken bond on the p side to complete it. So here we have a broken bond, electron jumps and it fills this. So in this particular situation, if we see in terms of hole, electron is now here, and due to since electron is here, now we will have a broken bond here. In the next diagram we can see it like this. This bond is now complete and we will have a broken bond here. In terms of hole, this is a hole because there is a broken bond, and this broken bond is known as hole, and hole is now here. So obviously hole was initially here, hole is finally here. So hole is diffused from p to n in this fashion. Electron is freed from this bond in the n side and this jumps to fill this vacancy, and now vacancy is created on the n side. So obviously this option C is correct. Now the electric field is linear if the charge density is uniform. We have now space charge density, we have volume charge density here. Here it is a negative charge density, here it is positive charge density. So electric field will be linear, it will be linear function of distance if charge density is uniform. If this charge density is uniform, this is negative charge density, this is positive charge density. So electric field will be linear. And if we are interested in the calculation of electric field, we can use Gauss law if we know the charge density here. So if we know the charge density, we can use Gauss law to find the electric field in this depletion region. So this will come linear if the charge density is uniform, and charge density will be uniform for uniform concentration of doping. If in this region we have uniform concentration of doping, in this region if we have uniform concentration of pentavalent doping atoms, so in those situations the charge density will be uniform and electric field will be linear function of distance, or let us assume x is the distance. So electric field is a linear function of x, and if electric field is linear function of x or some distance, then to find potential difference we have to integrate the expression of electric field, and obviously if this contains x, so this expression of potential difference will contain x square. So then potential has parabolic variation. So we will have parabolic variation of potential difference. If we plot this potential difference, since we have a parabolic variation, so this can be something like this parabolic variation. Normally in the textbook it is just shown by a simple straight line. We normally don't see it a parabolic variation. So in the books you can simply see this straight line, but this is parabolic, this is curved. So there is a potential difference between these two, and this is the potential difference between the two. Delta V naught, we can say it. Potential difference, this potential difference acts like a barrier for diffusion of majority charge carrier. Now what is happening is, we talked about the process of diffusion. In process of diffusion we talked the holes are diffusing from P to N and the electrons are diffusing from N to P like this due to concentration difference. And now there is electric field, and this electric field will apply force on these electrons towards right. So movement of electrons towards left, towards P side, will now be difficult due to presence of this electric field. And in the similar manner, the force on the hole, the assumed positive charge, the force on these holes will be towards the electric field. So movement of these holes from P to N side, that means diffusion, will become difficult now. So in the presence of this electric field, the movement, or we can say diffusion of these majority charge carriers is now difficult. And we can represent electric field by this kind of potential barrier. We can also term this delta V naught as potential barrier, where delta V naught is the potential barrier height, and we know that this will act as a barrier for majority charge carrier here. Due to this electric field, the positive charges cannot go from P to N. Suppose the potential is increasing in a region, so positive charge cannot move like this. A positive charge cannot move by itself from a lower potential to a higher potential, because in that way its energy will be increased, and potential energy cannot be increased by electric field only. There have to some external forces which can increase its potential energy. So a positive charge cannot go by itself from a low potential region to high potential region. It can go other way around. A positive charge can easily move from a high potential region to low potential region. And since this is high potential and this is low potential, electric field is from high potential to low potential. So obviously positive charge will face force by electric field in the direction of electric field, so it can move like this. It can easily move like this, but it cannot move like this. So this potential difference or potential barrier is actually a barrier, and it is a barrier for this kind of motion of positive charge, but not this kind of motion of positive charge. So it is a barrier for diffusion of majority charge carrier. Still some energetic majority carriers are able to cross. Yes, there is a barrier, but some majority charge carriers may have kinetic energy sufficient to cross this barrier. So these electrons or this charge carrier will cross this barrier, and again we will have some movement across the junction, and this movement is due to diffusion, and this is commonly known as diffusion current, because some charge is flowing across the junction and flow of charge per unit time is known as current. So moment of majority charge carrier is known as diffusion current, and this diffusion current is obviously from P to N, because positive charge is flowing from P to N and negative charge is flowing from N to P. So there is a diffusion current from N to P. So this is the direction of diffusion current from P to N. The electric field and depletion region helps in migration or drift of minority charge carrier. As I said, this kind of potential barrier is barrier for this kind of motion of positive charge, but not for this kind of positive charge. So this is the electric field, and holes near the junction. Suppose a hole is near the junction, and now this hole can definitely feel the force due to this electric field, and now this hole can move here, and this is opposite from this diffusion. So this is a minority charge carrier here, and it can now make a movement due to this electric field from N to P side. In the similar manner, this electron can also move in this direction. So the electric field in the depletion region helps in migration of drift of minority charge carrier. So due to this, the current is called drift. Hole is moving from N to P, and hole is like a positive charge, so drift current will be in this direction. So there are two kind of current across the junction. One is known as diffusion. Diffusion is due to majority charge carrier, and this drift is due to minority charge carrier. So the electric field is helping drift, but it is acting like a barrier for diffusion. In this diagram, I deliberately show the width of this depletion region in some non-uniform fashion. Suppose this width is, let's say on P side, this width is x1, and this is the original location of PN junction here, and now from here it is, let's say, suppose this is x2. This x1 and x2 can be equal, this x1 and x2 can be different. In the diagram, if I have shown x1 is less than x2, so it is also possible that we can have x1 is less than x2. So this width on the P side is less than the width on the N side. Total width of this depletion layer will be x is equal to x1 plus x2. So x1 plus x2 is the total width. So in which condition this x1 is less than x2? So x1 is less than x2 in the condition, if x1 is less than x2, that this imply, or this will be possible in the condition when the concentration of acceptor atom on the P side, we will have concentration of acceptor atom. So concentration of acceptor atom is greater than the concentration of donor atoms on the N side. How this condition is working? Suppose we have more concentration of acceptor atom. If we have more concentration of acceptor atom, then to neutralize the electron coming from N side to this whole side, or neutralize means there is a recombination. So for recombining of all the electrons which are coming from the N side to P side, since this concentration is more, so in the smaller width we can have those number of holes which are sufficient for recombination for the electrons which are coming from the N side. And since this concentration is less, ND is less, donor atoms concentration is less, we have to have this width more than this width x1. So in this more width we will have those number of electrons which are required for recombining with this much hole. So if this concentration is more, this width required will be less. In this less width we will have those number of holes. Since this concentration is less, so we will require a more width in this side. So this is the case, and opposite also holds. If x1 is greater than x2, then this Na is less than Nd. So what is this width? If you want to see the relation of width, so this width can be remembered as, you can also remember, or you can just see how it depends on the various parameter, this width. So this width is given by this relation. I'm not going to prove in this lecture. This is twice epsilon. Epsilon is just the permittivity of this medium, and multiplied by delta V naught. This is the potential difference between the two, divided by this electronic charge, 1 by Na plus 1 by Nd. Na is concentration of acceptor atom and Nd is the concentration of donor atom, and this total width is equal to x. And you can see, if you increase Na, x decreases. If you increase Nd, then x also decreases. So whenever we increase the concentration, the width of depletion layer will decrease. So increasing the concentration of acceptor or donor atoms will decrease the width of the depletion layer. Let us take a question. In a PN junction, the depletion region is 400 nanometer wide. This is the width, and an electric field of this much exists in it. Find the height of the potential barrier. That means the potential difference between the two. So potential difference we can easily write V is equal to this E into D. Electric field is given as uniform here. So this is 5 into 10 to the power 5 multiplied by this 400 nanometer, 400 into 10 to the power minus 9. So this will come out as 0.2 volt. So this is the potential barrier height. What should be the minimum kinetic energy of a conduction electron which can diffuse from N side to P side? So this is our PN junction. This is the depletion layer. This is the PN junction here. So what should be the minimum kinetic energy of conduction electron which can diffuse from N side So this electron, which was diffusing freely when this depletion layer was not there, has to do some effort and has to have some kinetic energy, then only it can reach here, and it has to cross the potential barrier, because it is a majority charge carrier on n side, and majority charge carrier, for majority charge carrier, this electric field which is in this direction from n to p is creating a potential barrier. And what is that potential height? That potential height is 0.2. So it needs 0.2 electron volt, thus potential difference multiplied by this E. So in terms of electron volt, this much is the kinetic energy required for this electron to cross this barrier. The next topic is equilibrium of p-n junction. Suppose this is a p-n junction. Here is the p side, this is the n side, this is the junction, and this is the depletion layer. So we have studied that due to concentration difference, their hole and electrons are diffusing like this, and due to this there is a diffusion current in this direction, and diffusion current is due to the majority charge carrier. As the holes and electrons are diffused, there is a space charge density in this region, and due to this space charge density there is electric field, and this electric field promotes the motion which is called as drift, and in the drift the minority charge carrier are also moving across the junction, and this gives rise to the drift current. So drift current will be in this direction. As space charge density is increasing, drift current is also increasing and diffusion current is decreasing. So as the time passes, diffusion is decreasing and drift is increasing. A time will come when there is equality between the two. So when these two are equal, diffusion is equal to drift. At this particular time, after this particular time, there is no net amount of charge which is crossing the junction, because from this side and from this side the net charge flow will be 0. So net current will be 0. So there is no net current across the junction. So net current across the junction will be 0 in the equilibrium. So a p-n junction which is just lying on the table will not have any current. In the equilibrium, diffusion current and drift current are equal in magnitude, opposite in direction, so net current will be 0 here. Next topic, biasing of p-n junction. So till now we have studied in the equilibrium, the p-n junction has no net current. There is diffusion current, there is drift current, but both the currents are equal, and there is no net current across the junction. There is no bias. There is no bias means it is not favoring drift current, it is not favoring diffusion current, both are equal, and net current is 0. So it is unbiased p-n junction, which is not biased for one thing. It is not biased for diffusion, it is not biased for drift, it is equal to all, and both the currents are equal, and net current is 0. Biasing of p-n junction is of two types. One is forward biasing. What is forward biasing? If p side is given a higher external voltage, suppose this is a p-n junction here, just we can show it like a just block diagram, and suppose I connect the p side with a battery, and battery is terminal, this is positive terminal. So let us connect this p-n junction material with this much polarity. So if p side is given a higher external voltage than the n side as on the diagram, then it is called forward biasing. It is forward biasing of the p-n junction. In forward biasing, the barrier height and depletion width both decrease. So barrier height, that means potential difference, is decreasing. Due to this battery, we can say there is external field like this, and the internal field due to the space charge density was like this. So both are in the opposite direction. So this decreases the electric field in the depletion region, and also this decreases the potential barrier. Initially the potential barrier is suppose delta V naught, and if you apply this battery of V, so now potential barrier is of this height, it is delta V naught minus V. whatever we apply here, and this much is the now difference in the potential barrier height. Initially it was delta V naught. When it is unbiased, now it is equal to delta V naught minus V. Now obviously this much polarity, or this positive polarity connected with the p side, and this is the electric field generated due to this biasing. So obviously this electric field will favor the diffusion current, because if electric field is like this, so holes will easily diffuse from p to n side, and electrons are easily diffused from n to p side, and now the barrier height is also reduced. So diffusion current increases, but this increase is not like from Ohm's law V is equal to IR. This is a non-linear relation. So diffusion current increases non-linearly, but the drift current, since drift current is due to minority charge carriers, and there is no such increase or decrease in this minority charge carrier, obviously there may be some effect on drift, but the drift current remains almost the same, giving rise to a net current, because when it was unbiased, drift and diffusion both were equal, net current was 0. Now it is now biased. This kind of PN junction is now biased, and it is now biased for what? It is biased for diffusion. Diffusion is more than drift. So obviously diffusion current is now greater than the drift current. So diffusion current increases non-linearly, but the drift current remains almost the same, giving rise to a net current. So what is the net current here? This net current is I diffusion minus I drift. So this is the net current, and obviously this net current is due to diffusion. So this is from P side to N side across the junction. Now next is reverse biasing. Obviously reverse biasing is just opposite of this, and in this situation this is our PN junction, and we connect it like this. So in this particular situation, the electric field will increase, the width of the depletion layer will increase, and the potential barrier height is now like this. And obviously since potential barrier height is increased, diffusion will be now less than drift, and in this situation the net current will be due to drift. So it is I drift minus I diffusion. Normally drift current does not change much, just it has got some favor. It has got some favor due to this reverse biasing. So it is biased, and biased for what? It is biased for drift. Drift is more than the diffusion now. We can also remember a result for net current. So net current, we can remember it like this: I is equal to some I naught a raised to power, this is exponential, and now this is the charge, EVA divided by KT. K is Boltzmann's constant, T is temperature, minus 1. VA is the applied voltage, whatever voltage we have applied. So VA is the applied voltage. If applied voltage is 0, so e to power 0 is 1, 1 minus 1 is 0. So net current, see, this I is the net current, so this net current will be 0. VA is positive for forward biased, and VA is obviously negative for reverse bias. We will take it as negative. Next topic is IV characteristics graph of PN junction. If we take a PN junction and we apply a battery to it and analyze what is the relation between, or graph between, the current and voltage, we get the graph something like this. This graph is plotted for a silicon PN junction. So in this region there is a V which is positive, and this is for forward biased. In this region we have shown V as negative, and this is for reverse biased. So this is the diagram. In this diagram, this is the symbol for the PN junction, and we call it as diode. So this is PN junction diode. In this diagram it is forward biased. So this is the voltmeter which can measure the potential difference across it, and this is the ammeter which can measure the current across it. So if it is forward biased, and we have already seen in the forward bias the net current is due to diffusion. So initially as we increase this voltage, we are increasing the forward biasing. Initially there is almost no current, there is very less current, and after some voltage the current suddenly increases, and we say that now this diode is in conduction mode. Diode is now conducting, and for this silicon diode, this is 0.6. At 0.6 voltage, it is now in the conduction mode. So this is 0.6, 0.7 around. So the actual value is, for silicon, this value is 0.7 volt. This voltage, after which there is a sharp increase in current. This voltage is known as threshold voltage, and this threshold voltage is 0.7 volt for silicon diode or silicon PN junction. For germanium, this is equal to about 0.2 volt. We should remember these values. These values may be required in some questions, and some questions are already asked in JEE, which require these results to be memorized, these facts to be memorized. So this is threshold voltage, or also known as cut-in voltage. After this voltage, or at this voltage, the diode becomes conducting. It conducts. Conduction means there is a sharp increase in current. It has significant current after this voltage, and this current is of the order of milliampere. Now in the reverse bias mode, so V is negative, and if V is negative and we are increasing the reverse bias voltage, as we increase the reverse bias voltage, we can see the current is almost constant, and we have plotted this on microampere scale, and you can see it is microammeter, because net current in the reverse biasing mode will be due to drift, and drift is due to minority charge carriers, and obviously minority charge carrier are in minority, and the current obtained will be very less, and it is of the order of microampere. So usually we say that this PN junction is more conducting, or it allows current from P to N, but as we apply battery like this, so current is obviously going in this direction, but in this direction when we are allowing current is very less. So in this direction current is very less, in this direction current is significant. That means it is of milliampere range, it is of microampere range. And in current electricity, when we studied resistance, this is a resistance. If we apply battery like this, or if we apply a battery like this, there is no difference. If this is V, this is R. In this case also current is V by R. In this case also current is V by R. So in this material, or in this conductors or resistance, there is no difference if you connect battery like this, if you connect battery like this. But in this situation, if you connect battery like this to the same PN junction, if you connect battery again to that same PN junction, the scenarios are changed. In this situation, there is a significant current which is of the order of milliampere, and in this situation there is no or very less current which is of the order of microampere. So we say that this PN junction is behaving like a diode. A diode is something which allows current in one direction only. So this is like a diode. It allows current in one direction from P to N. If we try to allow current or try to flow current from N to P, then it has no significant current. So it is acting like a diode. Diode means allowing current in one direction only. There is no such case for resistances. So this is a special kind of material which is a PN junction. So we can see this is of microampere range, but we can also see from the graph at a particular voltage known as breakdown voltage. So this is breakdown voltage. There is a sharp increase in current. We say that there is a breakdown of the material, breakdown the PN junction. We will deal with this breakdown in couple of minutes. So this is some voltage. At this voltage there is a sharp increase in current, and this is known as breakdown voltage. So this is the current voltage characteristic graph for PN junction. We define a term of resistance for this PN junction. Obviously this resistance is not like a ohmic resistance which follows V is equal to IR. So we define a new kind of resistance popularly known as dynamic resistance. So let us define this term dynamic resistance. This is equal to delta V upon delta I. Suppose from here to here there is a change in voltage which is equal to delta V, and from here to here there is a change in current which is delta I. If we divide this to delta V upon delta I, this is known as dynamic resistance for this particular range of voltage or current. So this is dynamic resistance. Obviously, if you have to define a resistance, it is equal to the instantaneous voltage upon instantaneous current, but we are more interested in the dynamic resistance for a particular range. Since PN junction is conducting when it is forward biased, or it is conducting when the current is from P to N, so for forward bias we can say that its resistance is less, and in this situation it is not allowing any current, it is allowing a very less significant current which is of the order of microampere. So in this situation we can say that it has a very high resistance. So in this situation this diode has a low resistance, very low resistance, and in this situation it has a very high resistance. Now in ideal situations, normally in problems we have to take some ideal situation because the resistance of diodes are not given. If resistance of diodes are given in the particular situation, we can take those resistance, but if resistances are not provided, we take ideal situations, and in ideal situation in forward bias we can take resistance as 0. There is no resistance of this PN junction in forward bias. In reverse bias we can take resistance as infinite. And for ideal diode the graphs are something like this. We can just simply draw a graph like this. This is just like this, and in this region it is just like this. So for ideal there is no need to draw like this. We just draw line along this voltage axis or perpendicular to the voltage axis only. This is for ideal diode. So we have to remember, for ideal diode in forward bias resistance is 0. For ideal diode in reverse bias resistance tends to infinite. So we will have to take these resistances if resistance is not provided and it is said that it is ideal diode, or even if they forgot to mention the question, we have to take it as ideal diode if resistances are not mentioned. And if resistances are mentioned for forward biasing and reverse biasing, we have to take those resistances to solve the problems. The next topic is breakdown of diode. As in the I wave characteristic, we have seen that at a particular voltage there is breakdown and current increases sharply in the reverse biased mode. This breakdown occurs by two mechanisms. One is known as avalanche breakdown and other is known as Zener breakdown. What is avalanche breakdown? If applied reverse voltage is high and depletion region is wide enough, so applied reverse voltage is high, depletion region is wide enough, then electron may gain high speed so that when it collides with the valence electron, the electron is moving from one side to another side due to this high voltage, and due to high voltage it can acquire a very high speed, and due to this high speed when it collides with the valence electron, so it reaches on the other side, it collides with the valence electron, and if it collides with a valence electron, then it can transfer its energy to this valence electron, and that bond is broken, and the bond is broken, then this valence electron will reach to the conduction band, and in this manner a large number of electron hole pairs can be generated and current is increased sharply. So this collide with the valence electron, it knocks it out, and bonds are broken and electron hole pairs are created in a large number. So this is known as avalanche breakdown. So it increases current very sharply. The other mechanism of breakdown is Zener breakdown, and this mechanism of breakdown can be controlled by us. It says if PN junction is highly doped, so this is under our control. We can dope it heavily, we can dope it lightly. So if PN junction is highly doped, what is the benefit of this? As we know that as we increase the doping concentration, the depletion layer thickness will decrease. So highly doped depletion layer is very thin, and since depletion layer is very thin, if we apply a reverse voltage, then that voltage divided by the thickness of the depletion layer, it will give the electric field. So since this is a very thin layer, very thin depletion layer, electric field becomes very high. If electric field becomes very high, then the valence bonds are broken due to this electric field itself. So now the valence bonds are broken due to this high electric field. This is known as internal field emission, and electrons go to the conduction band. Electrons are now free and they go to the conduction band, and a large number of electron hole pairs are generated and the current increases sharply. So condition of Zener breakdown can be controlled by us. We can just simply do the doping heavily, and if we do the doping heavily, we can control the layer thickness and we can control the reverse biasing voltage in such a manner that our diode is in breakdown. And there are some applications associated with Zener breakdown. We deliberately operate some diodes in this breakdown voltage region, and there are some applications which we will study further. Let us take a question. The circuit shown below contains two ideal diodes. So it has mentioned it is ideal diode, each with a forward resistance of 50 ohm. If the battery forward biasing resistance is 50 ohm is given, so we will take this resistance to solve the problem. If the battery voltage is 6 volt, the current through the 100 ohm resistance will be, so this is the resistance connected with the battery. So obviously this diode, this has P and this is N. This is the symbol, standard symbol for a diode, and in this symbol the arrow represents the direction of current, and obviously the direction of current is always from P to N. This is P and this is N for this diode. So this P is connected with the positive side and this N is connected with the positive side. So this is reverse bias and this is forward bias. And in forward bias, this will be a conducting diode and this will be a non-conducting diode. It will not conduct any current electricity. So the circuit for us will be this diode. You can replace it with 50 ohm resistance in forward biasing. This is 150 given, and there is no current in this diode. This is 100. So this is the equivalent circuit, and current is equal to 6 divided by, this is 150 plus 50, this is 200, 200 plus 100, this is 300. So the answer will be 0.02 ampere. So this is the correct value. The next question, two identical capacitors A and B charged to the same potential 5 volt are connected in two different circuits as shown below at time t is equal to 0. If the charge on the capacitor A and B at time t is equal to RC is Q and QB respectively, then so in this situation the current will try to flow in this direction. So current will try to flow in this direction, and you can see this is in a reverse biasing mode and it will not allow any current. So there is no current in this circuit. In this, the current should be like this, and this is in the forward biasing mode and it will allow current. So it will allow current, it will not allow current. So it is not going to allow any current. There is no discharging will happen. So charge on this capacitor will remain same always. So it will have the same charge always. So the charge on this will be some potential difference multiplied by its capacitance, which is CV. In this circuit, this is in the forward biasing mode, and forward biasing mode it is not offering any resistance. So as usual it will discharge, and its discharging equation can be written as Q is equal to Q e raised to power minus T by RC, and this initial charge is CV, and at this is e raised to power minus 1. So this is CV by A. This much charge will be on this capacitor at T is equal to RC. So the option number 1 will be correct. Next question, the reading of the ammeter for a silicon diode in the given circuit is. So specifically it has mentioned this is silicon diode, and if silicon diode is conducting, then there will be a potential drop on this silicon diode and what is that potential drop on the silicon diode. So as we have discussed in the theory, there is a potential drop of 0.7 volt. So potential drop will be 0.7 volt if it is conducting. So we have to take this potential drop, and from here to here this is 3 volt, here to here it is 0.7, this is potential drop. So net potential difference will be like 3 minus 0.7 divided by the overall resistance. So I'm not going to take any resistance for this silicon diode, and for this we have to take 200. So this is the current, and on calculation it can be seen that it is 11.5 milliampere. So this is the correct answer.